Yes. And we are back. And we are live. We have 11 days. 11 days until we take this AP test. It's a bird, I think. I don't know. Anyway, so I have you today. Next week, I have you Tuesday, Thursday, and then I have you that Monday. So after today, there will be 3 class periods before we knock out this AP test. So let's continue with what we're supposed to be doing. Now, my ultimate goal for today is to finish reviewing probability, which we are going to do. And with that, I am going to be throwing, after today, I'm going to be throwing a probability minor at you, but we'll figure that out when the time is appropriate. I'm going to do that probably during 4th period at some point. But yeah, that will be kind of wrapping up probability, but we're going to continue reviewing probability in the second part of today's class period. But the first thing that I want to do, I need to take an inventory of what you remember about linear regression. Linear regression covered 4 chapters. I believe it was chapters 6, 7, 8, and 9 in the textbook. And it was a lot of information from a bit of time ago. So I need to take an inventory as to what you remember. So what I have lined up is a practice quizzes. I have a practice quizzes lined up for you to take. And from this quizzes, I'm going to be able to identify what aspects of linear regression we need to focus on when you guys come back to me on Tuesday. So the first thing that you're going to have to do, obviously, the first thing, if you do not already have them out, I'm going to need those Chromebooks out and open so that we can knock out this practice quizzes. Where are people today? Is there another AP test today? Which one? Which one? Bio. Yeah. But like I said, this is a practice quizzes. Just as a reminder, while you're getting logged on and whatnot, obviously there was a chi-squared assessment due today. I can see all of the wonderful ones that were turned in so far. Yeah, just a reminder, if you did not get that in, make sure you get that into me. It is late now. But for those of you in the chat, if you would be so kind as to leave a comment, that would be absolutely wonderful. And let me get you logged on to this quizzes. Again, just a practice quizzes. Designed for me to just figure out, okay, what do you retain about linear regression? Let's get logged on as quickly as humanly possible. While I update this. There we go. Where's my volume? I feel like my volume is muted or something. And it is. Let's get there. Doom. There it goes. Excellent, excellent. Oh. We can get logged on as quickly as possible. Did y'all hear the updated CDC procedures on mask wearing? Some of you did? Some of you didn't? Okay. Basically, like what the CDC is saying is like if you are vaccinated, then there are a lot of situations in which you don't have to mask anymore. You know, even on indoors with people and stuff like that. But obviously, private businesses are private businesses. Schools are still schools. In fact, I saw a notice from the governor of New Jersey, Phil Murphy, where he basically said that New Jersey's Department of Health are going to be reviewing the CDC recommendations and then making the decision for themselves. So we'll see what happens. I don't know. I'm still holding out some hope, some tiny sliver of hope that on the last day of school, we'll be able to come in unmasked. I don't know. I don't think it'll happen, though. But we'll see what happens. That's cool. All right, so there's what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 of you here. 23, 4, 6, 6 of you here. Got to get people logged on as quickly as possible. Okay, so I know you're logging on right now, and that's fine, but the code will be at the top of the screen. So after we get started, you'll still be able to log in. And for those of you that have not been able to log in just yet, make sure that you do, even if the game is started, because that code, like I said, will still be at the top of the screen. Let me get this thing going, and let's see how we do. Remember, this is just a practice. And just for those in the chat, if you haven't seen it yet, there is the code that I just put in, 712168. 712168. Oh, yeah. Get logged on as quick as you can. The code is at the top. This is practice. It's an inventory for me to determine what do you remember about linear regression. Holy crap. For those of you that are still working, there's about 3 of you still left working. I'm going to give you about another minute to wrap that up. Here. Oh. Put that back over here. All right. Ooh, there he is. Ooh. I'm gonna give you the chance to win. Yeah, you gotta have a chance to win.
Okay.
I'm gonna leave it right there for everyone to see. While he's doing that, I'm gonna give you some non-stat related information. I'll give you some calculator information. So these calculators I just went through with new batteries, they will not turn on. Apparently, remember when the school shut down in March last year? When they shut it down, they basically turned off all forms of air conditioning to this part of the building. They basically only kept it for like the main office, I think, or something like that. I don't even know. Long story short, the acid melted out of the batteries. These are like 5 This is like a hunky chunk of change. Like TI-83 calculators, you could buy one, like decent one, for like $50. Like this, like $250 right here. Done because somebody decided they didn't want to turn on air conditioning. Okay. But yeah, that's why they wouldn't work. And I wanted to throw them out in one swoop, but then I found an extra one. So did it work? Force only counts as worst grenades. But yeah, those are dead. But the ones that I did put back in the bag, they are good to go. I sanitized them. We'll talk about those in a little bit. How's he doing? Oh no. Can you still podium?
I'm on one.
Oh. All right, there we go. So you can't podium. I put the pressure on you. Okay. Okay. Wait, I thought, don't they usually show the top 3? No, code's dumb. Anyway, so I'm not going to go over all of the details of this LINREG thing with you right now, but I just kind of want to look at some of the questions that were the most difficult for you. So I sorted them by accuracy. I just kind of want to get an idea as to what it is that you guys may or may not remember. Ooh, interesting. Which of the following statements can be made on the basis of the computer output? A fisheries biologist. This is number 14, by the way, number 14, because you can still access the questions. A fisheries biologist studying whitefish in a Canadian lake collected data on the length and egg production of 25 female fish. A scatter plot of her results and the regression output, or the regression analysis of egg production versus fish length are given below. Note that number of eggs is given in 1,000, meaning 40 means 40,000. Which of the following statements can be made based on the computer output? Okay, I see the computer output. I see an R squared of 43.2. Okay. Interesting. What is going on with this question? It looks like most of you either picked the 83.5 or the 69.7, but then this 69.7, it sounds like they're giving an R squared definition. 69.7 of the variation in egg production can be accounted for by the linear regression of egg production on fish length. But it's not 69.7%. It should be 43.2%. What is going on there? Where did they get that number from? Unless there's some kind of conversion done, but that doesn't make any sense because the R squared should be unitless. There should not be any units on the R. It doesn't matter what your units are or what scale they're in. I'm fairly certain this is a messed up question. I'm gonna report that one. Oh. Yeah. Hmm.
Where are these? What?
Yeah.
I couldn't find any of them.
Because here's the thing. I understand about like the fish eggs being measured in thousands. I understand about all that other stuff, but R, the correlation coefficient, has no unit. It doesn't matter what the unit is. It doesn't matter what scale you turn the data into. When you calculate the R should be impervious to that. Thus, the R squared should be impervious to that. So it doesn't matter what they measure things in. This is the regression output. Huh. Yeah, I'm fairly, yeah. Goodness gracious. Then what's the difference between this one and the fourth one? The variation, okay. It was, they switched up the variables. Egg production, fish length, yeah, they switched up the X and Y. It's always the percentage of the variation of the Y variable can be accounted for by the linear model on the X variable. That's always the way that you can define R squared. And then, here's a good one. Consider the following scatter plots. What is the relationship? Ha ha ha! Nice. Do you know why the answer was none of these? What's that middle one? What's that middle graph? What's the R value for that middle graph? Nope. R measures how strong the linear association is. R, for example, on the third graph, the R value would be a 1. It would be a solid 1 because they line up in a straight line. On the first graph, the R value would still be positive. Maybe it'd be like 0.8 or 0.7 or something like that on the first graph. On the second graph, they also line up in a straight line. But what type of straight line? What? What type of line is that? It does have a slope of 0, but that's not what they asked for. They asked for the R value. Yes, the slope is 0. Yes, it's a horizontal line. But if that's the case, your calculator actually produces an error if you try to calculate the R value. It does. Hold on. I'll show you. Right. What is that? I don't want to sync that. Nope, I didn't want that. I hate technology and their batteries and all their stuff that they do. Here, zoom it in. Let's see, stat, edit, 1, 2, 3, 4, 4, 4, 4, 4. Let's take a look at the scatter plot. There's the scatter plot right there. Straight line, let's get rid of that. There we go. Let me turn on my diagnostics. Diagnostic on, boom. If I were to run a linreg, look at my R value. It's nothing there. Horizontal lines don't produce an R value. The R value is supposed to indicate the strength of the linear association, yes, but also it's supposed to indicate the direction of the relationship, either positive or negative. If it's not positive or negative, then it can't actually produce an R value. It's weird. One of those trick little questions. I'll look at one, maybe one more here. Which one? Oh, yeah, the R squared. The correlation coefficient is the R value. Thankfully, no one picked slope. The regression line itself, that's your Y hat. It is the coefficient of determination. It's not a phrase that we used often, but it is a phrase that we have used. So, okay. All right. I will go through that again with myself, and I will come up with some questions that we are going to review, both multiple choice and free response. We'll kind of figure that out as we go along. In the meantime, what I would like to do, I would like to continue with what we were doing last class. I want to continue with some of those probability problems. So now there's people missing today, which is good because now we can actually use all these calculators. Here's the thing. All the calculators that I just put into the bag, I put fresh, brand new batteries in it. There might be a battery in the other bag or a calculator in the other bag that when you turn it on, it'll say like, what did they say? Like low battery, change the batteries or whatever, something like that. I need to know that because I'm not going to be sending you guys into this test with a battery that's like half filled or whatever. So what I'm going to ask is that if you have your own handheld calculator, yes, by all means, continue using that for today. But for the rest of you, I would like you to kind of get used to the handheld calculators one more time. So if you don't have a handheld calculator and you're within these first couple of rows, please, by all means, come get one. They are disinfected, but I definitely need to see whether or not there are any like low batteries in need of change or something like that. No, I mean, you can take it back. Just use it, and then if it happens to pop up, you let me know later on. Okay, and you guys got your own. That's perfect. Does he got his own calculator too? Nope, that's a phone. Yeah, you got to get your own calculator then. Next couple of rows, go get them too. That'd be great. Like I said, they're just in the last couple of rows as well. Of course, go get them. Do you get your own calculator? Oh, sweet. Now, for those of you that have your own calculator, like I saw that one takes batteries, right? Yeah. For the ones that you guys have, are they the ones that take batteries or are they the ones that you got to charge? Okay. Yeah. I had a kid last year, not an AP stat, an algebra 2, who had his own handheld calculator. And he was so proud of it every single time. It was like an algebra 2 CP class. He's so stinking proud of this handheld calculator. He's like showing it off every time. I got my own calculator. Blah, blah, blah. Constantly, he forgot to charge that thing. And it was always dead. And it was just like, well, I would use it, but the battery, I haven't charged it in like 6 months. I'm like, just charge the thing. Please, just charge the thing. You do not want to be in the middle of the AP test and have either the charge die or the battery die or whatever. I can't. Goodness. I once lent a calculator to a student to take the SATs, and she came back and told me that it died within the first 10 minutes, and she did her entire SATs with a dead calculator. And I had told her before she left, please make sure you check to make sure the batteries are okay, number one. Number two, if you can, bring spare batteries. She did not do either of those two. I felt bad, but I did warn her. Okay. So my goal is the same as last time. I have some multiple choice probability questions that I'm going to be throwing at you. AP level multiple choice questions, of course. Let's see where this is going to take us. Oh, that is interesting. Okay, I'm going to put this here. I'm not going to say much about it other than read the question because I want to see what you interpret as a result of it. You win a game if you flip a coin with heads coming up exactly 50% of the tosses. Would you rather flip 10 times or 100 times? And then they give you all of these options. Take your time. Because even if you can narrow it down, if you're wrong, you're wrong. You don't get the credit for it. There we go. And I do have the chat open on my phone right here, just in case you guys have any questions. There are going to be a lot of questions on the AP test that you read and you think, oh, I got this. And then you immediately pick an answer and then you move on. And yes, that may happen from time to time, and you may be absolutely 100% correct. But you do have to be careful. Come back to that question. Read it again if need be. Get in the habit of rereading a question, even if you have selected an answer. Try to gauge how confident you are in selecting said answer. You win a game if you flip a coin with heads coming up exactly 50% of the time. Exactly 50% of the time. Now, you're either going to flip it 10 times or 100 times. Now, it appears to me that because of the option that they gave you in choice A, the 0.246 versus 0.080, it implies to me that there may be a percentage that I can calculate. Yes, I mean, the central limit theorem, and then they have these combination things, and then the law of large numbers, and then your chances are the same? Like, I don't know. What you really should be doing for this particular problem is you should be thinking of it as a binomial. There's two separate binomials that you can calculate. You can calculate it with 10 flips, and you can calculate it with 100 flips, and getting exactly 50% success. So if I'm going to go binomial, keep in mind I got to pick binomial PDF. PDF would be getting exactly that many successes. 10 flips, 50% chance of success, and getting exactly half of them, I have about a 24.6% chance. Now, all of a sudden, it's like, oh, now I know what the answer is. Well, just for the sake of argument, I'm also going to do binomial PDF 100, 0.5, 50, getting 50% success. And it comes up as about 8%. 795 rounds up to 0.080, which means that your answer is indeed A. A lot of those answers seem like, yeah, well, maybe that, and maybe that, maybe that. But if they give you decimals like that, perhaps you should go about the calculation, because that calculation may end up helping. And that definitively proves it. Yeah, you have a higher chance of that happening. Now, why is that? If you think about it, it's like, well, no, I thought if you flipped it more times, the closer you would be to 50-50. Yes, absolutely. That is 100% true. You got to get exactly 50-50. Yeah. More likely, if you flip it 100 times, you might get 52-48, 51-49, 53-47. Those are very close. there are a lot more opportunities to just miss 50-50, to just miss it if you flipped it 100 times. Versus if you flipped it 10 times, dumb luck, I got 5 out of 5. Or 5 out of 10, I should say. I shouldn't say dumb luck. It's not actually. But yeah, there's a higher chance of that happening. And yeah, there's a higher chance of you getting like 8 out of 10. It's not as likely, but getting 5 out of 10, yeah, we get about a 25% chance of that happening. Now, compare that to this. Check this out. I'm going to do something real quick here. Let's say 0.4, 0.6, 0.5, square root of 0.5 times 0.5 divided by 10. I'm trying to figure out the probability of getting between 40% and 60%, given that I have an average of 50%, and I'm only flipping it 10 times. The chances of this happening are about 48%. But if I now flip this thing 100 times, I have a 95% chance of that happening. Yeah, if I flip a coin 100 times, I have a 95% chance of getting between 40 and 60% heads. Yeah, you do. Absolutely. But if you only flipped it 10 times, you only have a 47% chance. This, what I have calculated on the board, exemplifies the idea of the law of large numbers. The more times you flip it, the more likely you are to be around the average. But getting exactly that many, calculate the binomial PDF. And you'll see what the chances are of getting exactly that number. It's like hitting a dartboard directly in the middle. Like, you hit the bullseye, but the bullseye is just a little bit wider, so you hit kind of like the side of the bullseye. All right. Weirdness. I'll come back to that one. Ooh. This is an amazing problem that we're going to have a conversation about. Suppose two events, E and F, have a non-zero probability, P and G respectively, meaning the probability of E happening is P and the probability of F happening is Q. Which of the following is impossible? I'll kind of zoom in a little bit on those. Which of the following is impossible? You have your answer that you may have chosen, but I'm going to do something right here. They do not say what the relationship is between E and F. They don't say if they are complement or complements of each other. They don't give you any of that information. They just label them as P and Q. Now, if the probability of E is P, you could say maybe this is like, like 0.6. And the probability of F could be 0.5, meaning if you added them together, they would be more than 1. It's possible. I mean, I don't know why you would add them. But if this were the case of these two events, then yeah, that's possible. What if you subtract them and being less than 0? Well, it could be less than 0 if the probability of F was like 0.7. Then yeah, that's also possible. Cool. What about P divided by Q being greater than 1? Yeah, that could happen. If it was something like that, absolutely. That'd be greater than 1 if you divided them. The answer is not A, B, or C, is my point. You can come up with scenarios within the confines of the problem to be able to show, like, yeah, it's possible. That could happen. That could absolutely happen. So it can't be A, B, or C. Comes down to D or E. You have to remember your definitions of independence when it comes to probabilities and being mutually exclusive. So I'm going to take a moment and I'm going to step back to my notes real quick. If you would, if you do not already have them out, I would recommend that you get those notebooks out and open. I'm going to put something into my notes. Zooming out, zooming out. This is just my probability review continued from last time. Today is the 14th. Yeah, it is. If, I'm going to call them A and B. If A and B are independent events, then you could say a couple things. You could say either the probability of B is approximately equal to the probability of B given A. That's one thing that you could say if they are independent events, meaning that one does not affect the other. Or you could say the probability of A and B is equal to the probability of A times the probability of B. Just flat out multiply the two of them together, and you would get the probability of A and B. That and implies multiplication. Versus if A and B are mutually exclusive. If they are mutually exclusive, another word for that, which I know many of you remember, is disjoint. If A and B are mutually exclusive, then the probability of A and B is equal to 0. That is the pure definition as to what it means to be mutually exclusive. So now, going back to the question itself, the multiple choice question, what may be the answer? Now, again, something we have to keep in mind about these two events. The two events in question on the card do not have a 0 probability. The two events on the card are non-zero probabilities. So if the two events are independent, then, well, this would actually get you a numerical value, this calculation, versus if they were mutually exclusive, that's not possible because there's no way that would be equal to 0 then. I go back to the card. Which one is impossible? It's the last one. If this is the scenario that has in place where they are non-zero probabilities, then they cannot be both independent and mutually exclusive at the same time. It's impossible. And you can see that on the back of the card here. They use that symbolism right there. Oh, they did the exact same thing I did, kind of. Yeah. They probably said it a bit more eloquently than I did. Anyway, that was that one. Oh, here we go. This is a fun one because it's chi-squared. which of the following are true statements about the chi-squared distribution? Now, I have not talked a lot about what the chi-squared distribution looks like. I want to see what you guys believe about it or have read about it. Which of the following are true statements about the chi-squared distribution? I'll give you some time to read that. If you are ever faced with a question on this AP test where you find yourself saying to yourself, well, that's a weird statement. You find yourself saying, holy crap, I have absolutely no stinking idea. What do I do? This is what? Don't fret. Try to take as much of a logical approach as you can. But in the end, do not leave it blank. Do not leave it blank. If this is a question where you're just like, oh, my little kind of thing, then again, there's probably a good number of people in the country at the same time thinking the exact same thing. If you go on Twitter, both before and after the AP Stat test, just search on Twitter AP Stat, you're going to see a lot of people freaking out about the AP test. And then either you're going to be one of them or you're going to be like, what are they freaking out for? There's a lot of information that hasn't exactly been covered, but this is one that you can still potentially get correct. If you took a guess, maybe if you just pick one of those letters right now, try to make as logical a statement as possible. Let's see if you're correct, and then we'll read the back. The answer is D. For the T distribution, which by the way, the answer D was all of them are correct. For the T distribution, there is a separate chi-squared curve for each degree of freedom. Yeah, anything that has like degrees of freedom like that would definitely have a separate chi-squared curve. What statement was that? That was statement 3. That was statement 3 being correct. Meaning if you believed that statement 3 was correct, you could at least go from 20% chance up to a 25% chance by eliminating choice A. The rest gets a little bit dicey though. And like the T distribution, for large degrees of freedom, the chi-squared distribution is more symmetric and bell-shaped. Well, yeah, as the sample size grows larger, the thing becomes more and more normal, so to speak. If you wanted to even make that kind of statement for the first statement saying that that was correct, that would eliminate choice C, and you would be down to B and D. Now, in terms of part 2, again, we haven't really talked about that. And in fact, the back of the card doesn't really talk about that either. So that would just be one of those pure guesses that, who knows? Perhaps you can be like that student I had a few years ago who somehow got a 3 just based on amazing multiple choice skills. It wasn't just flat out, I'm going to guess on every problem. It was more along the lines of, let me make an educated guess. Educated guess. Okay. Let me back up a little bit to some of these earlier problems to kind of give you some reminder of a kind of a hodgepodge of stuff. This is now kind of like different types of probability that I'm going to be throwing at you. I'm not going to tell you what to do, but I'm going to have you do this one. The television game show has 3 payoffs for the following probabilities. What are the mean and standard deviation of the payoff variable? I'm not going to tell you what to do. I'll let you do what you need to do. Let's see. I look at this problem, and it doesn't actually use the one word that would be incredibly helpful for getting this answer immediately. And that would be expected value. Or 2 words, I should say. 2 words that would help you kind of get to that point of, oh, I vaguely remember how to do expected value. I think it's like if you take the payoff and multiply it by the probability and then do that for all 3 of them and then add them up, you'll get the mean. Yes, you will. But how does one get the standard deviation? Oh, my screen froze. Left my heart. There we go. How does one get the standard deviation? Oh, here's the easiest, absolute easiest way to go about it. If you type in that information into L1 and L2, the payoff and the probability of that payoff happening, and then you run a 1-var stat, but not just any 1-var stat. Now, on your calculators that are on your computer, and I'll bring this up in a moment, it does have a different type of interface. But if you're using my handheld calculators and you get something like this, if you want it, that's not us. If you want it to do it correctly, you have to type in L1, comma, L2. You have to make sure you type in L1, comma, L2. By doing that, you're forcing 1-var stats to do what the Chromebook calculator would do, and it would calculate the expected payoff, and it would calculate that standard deviation. You see that the answer is B. The answer should be B on this one. And yes, indeed it is. Now, on the back of the card, they show you actually by hand how to calculate that thing, but you don't have to do that for multiple choice. You wouldn't even have to do that for free response. For free response, you can just literally tell the AP grader what you typed in. And then that will spit out that appropriate mean and standard deviation. For the sake of argument, if you were to do this here, let me clear that out. Second plus sign 712. If you were to type it in here, 0, 500, 5,000, 0.7, 0.25, 0.05, and then do the 1 bar stat, it would give you this interface. But as we discovered, the frequency list, you need to type in L2. And it will give you those numbers. Huzzah! Okay. Get back here. This thing. Click, click. That was that one. Okay, now it's time. I mentioned this last class, and I am going to put something into my notes about this, but I want to see what you do first. This is going to be amazing. A travel agent books passages on 3 different tours, with half her customers choosing tour 1, a third choosing tour 2, and the rest choosing tour 3. The agent has noted that 3/4 of those who take tour 1 return to book again. 2/3 who take tour 2 return, and 1/2 who take T3 return. If a customer does return, what is the probability that the person first went on tour 2? I'm going to leave you to this one for a little bit. This problem might take a little digging. It might be more complicated than you think. I'm also going to recommend that if you want to organize this information, perhaps you draw a probability tree. That may be in your best interest. All right. I'm going to start drawing something. I'm going to put this into my notes with this problem. Let's see here. I'm going to leave it up on the board for a moment while I draw this so people have the opportunity to continue looking at this problem. But it says that half of the customers take tour 1, a third of them choose tour 2, and the rest of them choose tour 3. So if you're just doing this the easiest way possible, if you're doing this in the absolute easiest way possible, I would do something like this, just so I don't have to think too hard about what that fraction is. If I'm taking away a half and a third, the remainder would be a sixth. I don't know. Without having to think too hard, using the calculator to my advantage. And then it says 3/4 of those who take tour 1 return to book passage again, and the rest don't. And then if they took tour 2, 2/3 of them return, and the rest don't. And then a half of those who took tour 3 return, and the rest don't. So let me zoom out and show you what I drew. Zooming out, zooming out, zooming out, zooming out. This is what I drew to organize my information. This is my probability tree. This probability tree will absolutely help with getting this answer in the easiest, most efficient way possible. Just have to realize that going down the probability tree indicates a lot of things. For example, if I wanted to do the probability that the person returned, given that they went on a certain tour, let's say, let me actually work this out a little bit. Actually, no, I'll draw it on the board so I can erase it. It's easier to do it that way. If I wanted the probability of the person returning, given that they went on tour 1, that would be 3/4. That's what that statement is actually saying. Given that I've already gone down the branch of tour 1, what is the probability that the person returns? 3/4. Whereas if I wanted to do the probability of T1 and returning, I would have to multiply together 1/2 and 3/4 to get 3/8. It's an 8. There we go. So it depends on what the question is asking that will allow you to get a specific answer. But now, what is the question that is being asked on the card? The question that's being asked on the card is, well, if the customer returns, what is the probability that they went on tour 2? Well, hold on a second. The probability of returning given tour 2, well, I already know that. That's 2/3. But that's not what the question's asking. That's not what the question's asking. The question is not asking the probability of returning given tour 2. The question is asking what is the probability of tour 2 given returning. Let me put that question back up there to kind of exemplify this. Oh, zooming in. Look back at this question. It'll focus in a moment. If a customer does return, given that the customer does return, assuming that the customer returns, what is the probability that they took tour 2? That's what the question's asking. What is the probability that they went on tour 2 given that they returned? This chart, just by looking at it, does not give me the answer, but it will help me get to the answer. If I want to do this, I'm going to need a formula, and I'm going to write this formula on my next page and then go back to this chart right here. The formula that I need is this. The probability of B given A is equal to the probability of A and B divided by the probability of A. You need that. You need that, you need that, you need that. That formula is given to you on the formula sheet for the test. It is. It's just given to you slightly differently, but it is the exact same formula. Now, how do we use that for this particular problem? Well, let me go up here real quick. If I am going to do the probability of T2 given a return, then I have to calculate the probability of T2 and return divided by the probability of returning. That's what I'm going to have to calculate to get this problem done. Well, this is stuff that, again, we've done in the past, but it's been a while. So what I'm going to have to do with this chart, first, let me do T2 and returning, and let me multiply the two of them together. The probability of T2 and returning is the fraction 2/9. Write that a little bit. I'm going to write that bigger. 2/9. That's the probability of T2 and returning. I'm also going to calculate the probability of T1 and returning. That would be the fraction 3/8. And T3 and returning, which would be the fraction 1/12. I need all three of those fractions to get this problem done. I need all three of those fractions to get this problem done. 3/8, 2/9, 1/12. Because all three of those fractions represent the person returning. The person could return given they went on T1. They could return given that they went on T2. They could return given that they went on T3. If I were to add all three of them together, I would get the probability of just flat out returning. So on my little page right here, if I'm going to calculate the probability of T2 given a return, it would be 2/9 divided by 3/8 plus 2/9 plus 1/12. That would be the calculation that you need to get done. That would be the calculation that would get your answer. Then I would finally go to my calculator. Say, okay, 2/9, be careful with how you're typing this in, divided by parentheses 3/8 plus 2/9 plus 1/12 parentheses Chateau. Now, of course, if you looked at the card, all of those answers were written as fractions. Of course, you can always hit math frac, math enter, enter to get that final answer. 16 out of 49. This is the type of question where if you had no idea that a probability tree would be helpful, you might just blow right through this one, not even care about it. All right. But if you kind of knew what a probability tree was and how to use it and how to exemplify it for this answer, it may take you a few extra minutes to get this thing done, and that is okay. That is perfectly fine. If I actually look at the back of the card, you can see they drew a more simplified version of the probability tree, but it is the exact same calculation that was gotten done. It's incredibly helpful to do this. Incredibly helpful. Let's try one more, and then we'll wrap up for today. Let's see here. I don't like that one. Oh, here we go. Something similar. Something incredibly similar. I'm just going to leave this for you right here. Suppose P of X equals 0.25 and P of Y equals 0.40. If the probability of X given Y is 0.2, what is the probability of Y given X? I'm going to let you ponder that for a few minutes. Couple of things. First and foremost, they don't really give you that much information. They really, really don't. This is what they give you right here. I'll zoom out. There we go. This is what they give you. Now, I know that relationship of, okay, the probability of X comma Y should be equal to the probability of X and Y divided by the probability of Y. That relationship is right there for the taking. You always divide by the probability of the given event. But you know what some of these decimals are. You know what this is 0.2 and this is 0.4. And if you multiply by 0.4, you can get the probability of X and Y. 0.2 times 0.4. Oh my. Why am I getting a syntax error? There it is. It's 0.08. Why don't I just do that in my head? But they want, what is the probability of Y comma X? Well, if that's the case, if they want the probability of Y comma, or Y given X, I should say. I don't know why I keep saying comma. If they wanted that, then it would be the probability of both divided by the probability of X. Doing that calculation gets me a 0.32, which that answer is C. It's utilizing that formula to its fullest extent, being able to manipulate the way that the relationships are in order to force out a correct answer. Probability is messed up. Okay. Like I said, I am going to be throwing a probability assessment at you. Probably do that later today at some point. But then on Tuesday, when you come back, we will be reviewing linear regression. I will have some free response questions for you to go over those. Because linear regression can be a bit tricky, especially since we have not seen it for a while. We probably haven't done linear regression since like December, possibly. I don't know. Anywho's, if you're in the chat, I see those of you that have commented so far. If you haven't commented, please make sure that you do so. The bell is going to ring in approximately 90 seconds or so, but we'll kind of finish it up there. If you have one of my calculators, please make sure you just wipe it down real quick before you put it in the bag. That would be fantastic. And then I will work on getting new calculators, and we'll see if I can get enough. I'm going to leave the chat open just for maybe another 30 seconds or so.